Okay, so who am I? Why should you care about anything I have to say? This is me. My name is Jon Avezbaki. I guess former software engineer. I worked on trading chatbots, banking mobile apps, autonomous vehicle systems, tons of different things. I now work as a developer advocate and a full-time tech enthusiast, hopefully powering developers such as yourselves. Without further ado, let me go over the agenda. So this is the beginner level stuff. I'm sure probably 90% of the people in this room already know this stuff, but I'll go over it very, very briefly just to make sure anybody who doesn't code for a living is all caught up. Then we have the more intermediate levels that we'll be going over. This is where it actually starts to get more search engineering-esque and less computer science 101. And then finally, we have the fun AI stuff, or AI adjacent in some cases. So yeah, let's get started. All right, level 1 linear search. You're in a classroom and your teacher has asked you to open an arbitrary page. One way you could do this is linearly. You could start from page 1 and then 2, 3, 4, 5. You guys know that that's a horrible idea. It would take you forever to do this. It's awful, it's slow, brute force, O-of-N. More importantly, it doesn't leverage the fact that the book is ordered. So the solution is binary search, and probably this is closer to what you would actually do in the real world. If you're aiming for page 72 in a 200-page book, you can roughly start in the middle, you can overshoot a little bit, go back, then go forward, go back, et cetera, until you hit page 72. That's the way software would typically do search over an ordered data set, and that's what you do in in the real world with anything tangible. And level 3, hash tables. So if you want, going with our book example, if you wanted to find out what page chapter 2 starts on, you know that you can pop open the book to the table of contents. So in this case, you can see I have a pizza cookbook here, and chapter 2 starts on page 26. This is exactly the way hash tables work. It is a one-to-one mapping between the data you have and the data you want. If I go to a code check and I get back the number 98, and then I come back later that day, whoever's manning the code check knows which code is mine based off that number. License plate numbers, social security numbers, credit card numbers, they all work basically the same way. They're a one-to-one mapping between data that you have and data that you want. This is the way software works exactly. I'm not going to go into the math of hash tables here, since that isn't totally relevant for our goals today, but hopefully this is clear to anybody who doesn't work with software on a daily basis. Okay, level 4, inverted indices. So again, running with our book example, and for the purposes of everything that we're going to do today, let's just say that all of our examples are going to be pizza related, which is fitting given what we're serving today. So let's say that I need every pizza recipe in this book with mushrooms in it. How do I find that? You know that you can open the back of the book and find the index. And just like that, I now know that all the mushroom recipes are on page 34, 52, and 63. This is exactly the way an inverted index works in a software system. If you are building out the search system for your new email system and you need to let a user search for appointments, for example, an inverted index can very easily find all of the emails that have mentions of the word appointment in it. So unlike a hash table, it is not a one-to-one mapping, it's a one-to-many mapping, which if you're trying to build out a software system for search, that's usually pretty relevant because you don't typically want just one result. You want the most relevant 50 or 500 results. So thinking about things in a one-to-many mapping makes more sense as we get deeper and deeper into software-based search. Okay, level 5, TF. TF is a search algorithm, and like all of the algorithms we're going to go over today, they're very acronym-based. So let's break down the acronym. So TF stands for term frequency. Pretty straightforward. What does that actually mean? It's just how often a term shows up in a document. So if I have a recipe and the term, if the term artichoke shows up 50 times in that document, the term frequency for that is going to be 50 or 5 or however many it's showing up there. So again, I run a search for tasty artichoke pizza recipe, presumably in some kind of recipe database system. And so how will the TF algorithm score different recipes for this query? So I have recipe A and recipe B here. And you're probably immediately thinking, why am I looking at a vanilla birthday cake recipe? I searched for artichoke pizza, it's not birthday. Well, this author cleverly snuck in a couple of mentions of artichoke pizza right there. The recipe is ultimately for birthday cake, but for the event that they're serving the birthday cake at or that they baked it for, somebody served artichoke pizza. So that's going to kind of mess up our search a little bit, and why it's, we're even doing this comparison in the first place. So if we actually crunch these numbers between this, very minimal, straight to the point recipe and, sort of this keyword stuff one, we're going to get these numbers. And these are just counts of the number of times that these different terms show up for each recipe. And just for clarity, why do we care? Why do we care about, why do we need a scoring algorithm? Well, it's because, like I said before, we're thinking now in terms of getting back multiple results to our search queries. You don't really ever want to for users, this is the one and only artichoke pizza recipe I have. I want to see all of the ones that you have. I want to see every artichoke pizza recipe that you have. And so you can see that if you count up these frequencies for each word that makes up our user query, it doesn't look good. Recipe A got a total score of 12 and recipe B got 5. So we are now serving birthday cake recipes to our user for artichoke pizza recipes, which is unfortunate and not great. So the natural question is, how do we fix this? How are we going to win back this user? That is through another search algorithm known as IDF. Like I said, we're going to be acronym heavy today, but I will break down all the acronyms. So what does IDF stand for? It stands for inverse document frequency. And what does that mean? It's just how rare a term is in our database. So for example, if I'm, you can think of it like, again, if we're going to run the cooking example, cheese is probably going to show up in a lot of recipes. So it's not going to have a high IDF score. Cheese is going to be in, however many recipes. But if I'm, if I have if I want to assign an IDF score to a term like mussels or something, that's probably only going to be in like seafood-based recipes, which is going to make a much smaller subset of everything. So it's going to have a higher IDF score. So let's drill into a little bit more, what this means and how it works. So again, the frequency of a term is inversely proportional to its IDF score, hence inverse document frequency. Running with pizza again. So let's think of terms that would have very low IDF scores. Slice, pie, peel. Everybody in this room has heard of these terms. These are very common terms, so they're going to get very low IDF scores. They're not rare, and especially if we're exclusively looking at pizza recipes. Now, if we look at char, hydration, crumb, now we're getting into sort of pizza nerd territory. If you are a baker or you got into making sourdough during COVID, you've probably heard of these terms. And now if we go to leoparding, poolish, window pane, these are progressively even more advanced baking terms. These are not something that you're going to see in, my weeknight, pizza recipe or whatever, where it's like making pizza in 20 minutes. This is something that really a baker would use in their terms. So we have two different algorithms now, TF and IDF. And I want to revisit recipe A, but now using both of these algorithms instead of just the one. So again, just to review, recipe A got a TF score of 12 and recipe B got a TF score of 5. So these are these scores again. So recipe A, again, this is for cake. How are we going to get these IDF scores for, what the terms that the user put in? Well, tasty and recipe are borderline useless. Probably every recipe in my database is going to have the words tasty and recipe in it. So those are completely useless. And they're going to be very common across our entire recipe search database. So they're going to get very, very low IDF scores most likely. Now, artichoke and pizza are a little bit more rare. Artichoke especially doesn't, show up all that often in various recipes. And, pizza is a common food, but it's primarily only going to show up in the recipes that are for pizza and, hopefully not birthday cake. So what are we going to do? Now we have a TF score and IDF score. We're going to multiply them and we're going to get the product for both of those scores. We're going to add them up and we're going to get a new score, a final score of 19.2 in this case. And so if we apply the same math to recipe B, which was actually for pizza, we get a score of 26.6. So this is much better. We want ultimately recipe B to rank higher than recipe A. Recipe A is not what we want to give in this case. So presumably now, if I implement this in my recipe search system, a user is going to get recipe B up here and recipe A down here, which again is what we want. Ideally, we don't want recipe A at all, but having a lower score is better than nothing. Okay, level 7, BM25, again, new acronym. So BM25 stands for Best Match version 25. Why version 25? From my understanding, it's just the people that made the algorithm. It took them like 25 iterations to get to this particular version of the algorithm. So that's all it means. So what is it? It's literally just TF and IDF with some more bells and whistles. Let's go over those bells and whistles now. By comparing two different artichoke pizza recipes. So yeah, you're good.
Guys, sorry for the interruption. Fire department is going to do some testing inspection today. So you might hear the fire alarm go off. If it goes off, it's just the fire department doing some testing. Okay, I'm very sorry for the inconvenience.
You're totally good. Thank you for letting us know.
Yeah.
Okay, so we have recipe B, which we just saw, and recipe C, which is almost exactly the same. They're both, very minimal, but if you notice, there's some links I've snuck in at the bottom of this recipe here. So instead of, it's going to have more mentions of artichoke now because I'm mentioning other artichoke-based recipes here. Good SEO, but not terribly good for, search engineers. Let's look at another recipe, recipe D. Again, this is the exact same recipe. There is no difference. But again, this the author here decided to introduce the recipe with their time in Italy and all the different pizzas they tried. So now it's going to have more mentions of pizza in this case, which is not great. BM25 is going to let us combat both of these scenarios directly. So improvements over TF and IDF. A saturation curve is now applied to how term frequencies are calculated. And what exactly is a saturation curve? I play this little video here. Okay, so all this really means is that you're going to see, yes, sorry.
That kind of reminds me of Euler's number.
I'm sorry, I don't know what that is.
It's in calculus. It's like, I forgot what it is. It goes around like 2.3 something.
Oh, interesting. Okay, that was intentional, but that's, I guess, funny coincidence. In this case, all the saturation curve is really doing is it means that you are going to see diminishing returns the number of times the word artichoke is mentioned. So if I mention it 1 time versus 2 times, that is going to significantly move my score. If I mention it 27 versus 28 times, that's basically going to do nothing to my BM25 score. And this is useful because if I add 100 mentions of artichoke at the end of my artichoke pizza recipe, that should not be a way for me to gain whatever search system my recipe is going into. So that is essentially how the saturation curve is working. The other improvement is that it's going to take document length into account. So the guy that introduced his recipe with his time in Italy and all that fun stuff is no longer going to get the boost in our search system that he thinks he's going to get, hopefully. Okay, level 8, text analysis. Okay, so text analysis has a few different forms, but it all starts with tokenization. Tokenization is all about breaking down a query into individual tokens. Now, you might be thinking, why do we need to go over this? If someone's searching for tasty artichoke pizza recipe, just use a white space delimiter, and I have 4 tokens, done deal, no, don't need to think about it. That naive approach can work for some queries, but you're soon going to find that doesn't work for a lot of different queries that you're going to get. So let's take a couple of examples. So brick oven pizza. Am I including the hyphen or am I not including the hyphen? This will, meaningfully affect what results I'm getting back. If I type in how to make into a search bar, am I including the punctuation? Do I want the question mark? And apostrophes. If I'm looking for Danny's Pizza, if that is a chef that has made a famous pizza recipe, or if that is the name of a restaurant that I'm looking up, do I want the apostrophe or not? Other examples. In the Thai language, there are no spaces, and Thai is not unique in this way. There are other languages that don't have spaces. So in this case, if I want to get individual tokens from that sentence there, I can't just use a white space delimiter. That is not going to work. If I am looking for path hierarchies, how am I, handling forward slashes, backslashes, things like that? Do I just want the root of that path? Do I want the full path? And if there's an email in there, this can really trip me up if I chose, for whatever reason, depending on the input I'm getting, to delimit by periods or anything else like that. I want that full email there. I don't want it to get garbled. And in this case, we are using various tokenizers from Elastic that are particularly tuned to specific inputs. So this is as much of a technical concern as it is a UX concern. What kind of data are you expecting from your users? Okay, stop words, the next phase of text analysis. These are words like the, of, and, as, are. These are obviously language dependent, but essentially they're all unhelpful filler. These words don't meaningfully tell us anything about what the user is searching for. Normally, the way that our search systems are going to work is we are just going to filter them out and not do anything with them. Stemming. Okay, so in the same vein, if I am looking up charred pizza, I don't care if someone's recipe says this pizza will have char on it, or I want lots of char on my pizza. I just want that concept. It doesn't matter to me how it's articulated. So the way that we typically handle this in search systems is using something called stemming, where you basically truncate a word to its root form, its stem form, as it were. So in this case, charred pizza is going to become char pizza in after tokenization. Synonyms. So it does not matter whether I'm looking for New York or NY style pizza. I want the same recipes. I shouldn't have to manually input all of those search terms to get back the actual recipes that I want. How are we going to do this? In Elastic, there are a couple of ways to achieve this. You can use the synonyms API, you can use the synonyms file, and you can do this inline with the token filter. And I'll show those examples here. So you can see both for the synonyms API and the synonyms file, essentially all you're doing is defining a dictionary in a file or a set, saying like this word has these synonyms. We can also do it inline here, which is basically what that is. There's the fire alarm. So you can see that New York is just synonymous with NY and NYC. Again, you can't like do this like blanket. In this case, if I'm building a pizza search engine, then that is something that I can reasonably anticipate that's going to happen. So again, this is as much of a technical concern as it is a UX concern at the end of the day. And spell check. So if a user mistypes, what they pizza as PIZA, I do not want to give back results for PIZA. Those are probably going to be nonsense, garbled stuff, and I want to be able to handle that. I'm sure all of you have seen this in your preferred search engine. So how can we do this? You can register incorrect spellings as synonyms. You can use fuzzy queries, which operate through Levenshtein distance, which I'm not going to go over today, but I imagine a lot of you are familiar with it, and if not, it's fairly easy to pick up. A system in Elastic called suggesters, and phonetic token filter plugins, which essentially work by breaking down words into how they are pronounced. So if a user knows how a word is pronounced, they don't know how to spell it, you can still get a match potentially. All right, let's put that all together. So I search for the best wood-fired Neapolitan pie. First, I want to get rid of that's a stop word that's not relevant to what I want to search for. It's completely useless. Next, I want to change, I want to do stemming. So fired is now going to become fire. Pie is a synonym for pizza pie. I don't want to get, results about apple pie or something like that. That is not going to be helpful for this user. And lastly, I don't know if anyone caught it, Neapolitan is that is supposed to be a K. So to review, we removed the stop words. We converted words into their stem form. We expanded synonyms. So pie is now pizza. And we performed a basic spell check. Okay, level 9, re-rankers. So how would search work in an ideal world? And that's like a legitimate question. That's not rhetorical. Like if you actually think about it for a second, how do you imagine search working in an ideal world? I don't know about you guys, but in my ideal world, there's one guy, read ranker. And what this guy does is he will get all the relevant documents for me. So if I search for artichoke pizza recipe, he's going to go in the back and pull out all the documents. And then he's going to read them. He's going to read each one, and he's going to rank them individually by, by relevance. So you have one person essentially doing all of this work. This is obviously not possible, but we can just do this for the first few entries. So again, if we think about this from a UX perspective, users are typically not going to page 24 of your search results, to try to find the perfect entry. It's been proven time and time again that they are spending the most time on page 1, maybe page 2 or 3, potentially 4, but after that, there's a very, very steep drop off in users engaging with the essentially the search results and giving them back. So what if we optimize for that? Read is still too slow. One person cannot do this, but a machine learning model isn't. So what we can do, and this is essentially how re-rankers operate, is that Reed is still doing exactly what he's doing. He can, grab, let's say if I ask him, hey Reed, give me the top, artichoke pizza recipes. He can give me the top 10 in ranked order and feed that into a machine learning model or train it in a variety of different ways. And essentially what the re-ranker will do, we'll just do a final pass through on the very first page. So the re-ranker isn't operating over the entire return set for the search results. It's just giving page 1 a little bit extra finesse, so to speak. So I know I've been throwing a lot at you guys. We've been moving very quickly. So I want to sort of illustrate how all of this works with one query, all of these concepts and levels that we've been running through. So charred crust artichoke pizza recipe. First, we're going to do text analysis. We need to break this up into tokens. We're going to do a basic spell correct. PIZA is obviously incorrect. It's supposed to be PIZZA. And again, charred is going to become char. We're going to use an inverted index. An inverted index is going to grab every recipe filed under artichoke, for example. So now we have a subset of recipes that are potentially relevant to what the user has queried for. Next, we're going to use BM25. So we have, let's say, 100 recipes. We don't want to give them back to the user in a random order. We want them to be scored in an intelligent way. So we're going to use a combination of TF and IDF plus the other bells and whistles that we talked about that BM25 comes with. And lastly, we're gonna have a re-ranker come in at the end and reorganize the first few entries so that they just look a little nicer, they're presented, you know, a little bit more cleanly. Any questions so far? That is basically everything that we have gone through. We still have a little bit more to go, but I just wanna add a little checkpoint here to see if there are any questions, comments, concerns kind of thing. Okay, cool, moving right along. Level 10, vectors. Okay, a vector is how a computer encodes abstract concepts. This is kind of a gross oversimplification, but hopefully we will get to a more concrete understanding by the end of this level. And I'm going to use Italian American cuisine as my example here. So we're still running with, you know, pizza or pizza adjacent examples. So let's say I graph, you know, a handful of different Italian American foods along this simplex. How do you read this? What exactly is this? So basically, each food is going to be closer to the vertex that corresponds with that ingredient and farther away from the vertices that represent ingredients that are not present in that food. So in this case, garlic knots are basically all dough. Maybe there's a little bit of cheese, so they're going to be a little lifted over there. Mozzarella sticks are basically just breaded cheese. So they're essentially going to hug the left side there. If you don't get any marinara on the side, there's going to be no tomato involved. If it's all tomato, it's marinara. And if it's equal parts dough, cheese, and tomato, it's going to be pizza, lasagna, and stuffed shells in the center. They're roughly equidistant from all three of these. And obviously, vectors are not going to, make you a nice, pretty diagram. These are going to be, graphed in vector space. So there's going to be a coordinate system that this corresponds to. Now, unfortunately, I can't, encode every single cuisine in the known universe, along this small simplex. I can barely do Italian American cuisine. I'm not considering whether protein is an element of a dish or really any other ingredients. So this is a gross oversimplification. In reality, this is going to look something like this. This is going to be along 100 or 1,000 dimensions. And I'm not going to be plotting these manually. I'm going to be using an embedding model or, an embedding model, and it's going to generate these vectors for me. And the way that they're going to be plotted is not going to be along human readable axes. They're going to be, only really machine intelligible. They're not really going to be, relevant to what we can read, but this is a very helpful way to understand what concepts are and are not related. So just by visually looking at this, you can tell that vodka sauce and marinara, even if you don't know what those things are, you can tell that they're, roughly similar. Same idea with stuffed shells and lasagna. You can also tell, if things are really far apart, that they're not related. Garlic knots and vodka sauce essentially don't really have all that much in common, which is useful. And we can do this just by measuring, doing some basic math and measuring the distance in coordinate space. It's a lot easier to do if it's, 3 coordinates, much harder to do if it's 100 or thousands of coordinates, but you're obviously not doing that math manually. Okay, so why do we care about vectors? Why did I go over that? What is the point of this, and how does that help us with search? That is what hybrid search is here to answer. So hybrid search is the fusion of BM25 and vector-based search. Essentially, we are still doing everything that we talked about before. We are not abandoning it. I want to emphasize that every level that I've been going over is essentially additive. You don't really abandon any of those strategies. You just keep stacking them on top of each other to make a more comprehensive search system, essentially. How are these going to be merged? That's through an algorithm called reciprocal rank fusion, or RRF. I'm not going to go over the math. We don't have the time for that. But essentially, I just want you to take away that this is the algorithm that is essentially the how we're going to merge these two disparate search systems. So this is what we went over before. This is still, like I said, this is the entire system. It still functions basically the exact same way, and except we are going to have BM25 and vector work together. And so how does this work practically in a search system? Imagine that your user, for whatever reason, has never heard of the concept of pizza, and they're like, hey, I had this cheesy flatbread. Give me a recipe for that. Vectors are what is ultimately going to help you or help your search system understand that cheesy flatbread is a synonym for pizza. You can't do that with BM25. BM25 is not going to work with things that are sort of that abstract. BM25 is great for things that are more literal, more exact keyword match-esque. Vector is good for conceptual understanding, things that are conceptually related but maybe aren't direct synonyms. So it's not that you always want to use hybrid search or you exclusively want to use BM25 or exclusively vector. These are system dependent. It depends on what are your users searching for. I talk to people every single day about how they're building their search systems, their RAG systems, and I see this common misunderstanding that you sort of have to there's one definitive way to build out these search systems, and that just doesn't work that way. It is always going to be dependent on the type of data that you house. So for this presentation, I've primarily been going over recipes, specifically pizza recipes for the most part, but you are always going to tweak this basic setup depending on what kind of data that you have, fundamental building blocks that you're going to be working with. Okay, level 12, RAG. So what is RAG? Again, I'm breaking down every acronym here. It's Retrieval-Augmented Generation. This is probably the term that I see really misused the most often. So I have seen people point to specific tooling or specific architectures as being RAG-based, and I think that is a bit of a misnomer and sort of playing fast and loose with the vocabulary. All RAG is a way to augment LLMs with something retrieval-based. That's all it is. It is a very large umbrella term. So why do we need this? Why do we care about this? So imagine that I have an LLM. It doesn't matter whether it's Gemini or Claude or whatever, but let's just say it was trained in 2025. A ton of data was fed into it in 2025, but I'm asking for the best pizza recipe of 2026. There is no way for that LLM to give me that data through, just through generation. It doesn't know about it. It'd be like asking Isaac Newton who's going to win the summer, Olympics of 1996. It does not matter how smart Isaac Newton is. He does not have that information, and he cannot give it to you. Same applies to an LLM. It does not matter how smart it is, how intelligent it is. It cannot give you that information. That is what the retrieval portion is essentially here to fix. So everything that we saw in that. So if you look at steps 2, retrieve, and then it goes to the web. It's essentially doing all of this. All of this is happening behind the scenes for any kind of LLM to essentially crawl the web, read everything, rank it accordingly, and determine what to give back to you. And that's essentially how it works. So it would do all of that, that whole pipeline that we just discussed, and that's how it would give you back that data. Okay, level 13, agentic memory. This functions very similarly, and I also see people regularly talk about this in a way that I think overcomplicates things or describes this in a way that isn't technically accurate. All this is really doing is making up for the fact that your LLM, whatever LLM you prefer, has a limited context window. So it does not matter if LLMs tomorrow have, a context window this big or this big. At some point, it will reach a limit on that, and it's going to need to search through some kind of conversation history to remember that. So let's say that I'm talking to an LLM for like an hour about making, a bunch of and my own custom artichoke pizza recipe. And I say, hey, do you remember that pickle pizza recipe you made for me earlier? Let's say that was like an hour ago. That might not be in the LLM's context window anymore. And it needs to go back into our conversation history and search through all of it. So again, it is going to be doing this entire process along our own conversation history in order to give me back that pickle pizza recipe that I had generated earlier. Now, I'm not claiming that this is exactly how ChatGPT or whatever does it, but this is the basic principle behind how it works. Same thing for RAG. I can't tell you exactly how your favorite RAG system works. All I'm trying to elucidate is that these are fundamentally the basic building blocks that you would need for these sorts of systems. And that's basically it. Are there any questions? Okay, thank you so much. Let me check in with our second speaker.
I'm here. I'm here.
Yeah, absolutely. Oh, sorry, I didn't notice that you came in.
John, I have.
Yes.
How do we decide like which algorithm or which type of search we wanted to go for? Like throughout the way we are trying to improve our search. There might be vector search which might be working best in one use case. Should we go ahead with the hybrid search, or should we stay with the vector search?
Gotcha. So it's all going to be dependent on what kind of I guess data your users are searching for. So let's say that you are Walmart and you want to create a search system. If this is like an internal database and you want people to be able to search by like product ID, product ID is not going to work well with vectors. Product ID does not make sense for that. You want BM25 for that because that is a very specific like keyword-esque thing. You are looking at a string literal. Encoding product IDs into a vector database does not make any sense. But if you want someone to search for, I'm looking for a plastic doohickey with 4 legs and a flat surface because I don't remember the word for table. That is something that vectors would be good at. Vectors are good at conceptually linking those two ideas together. So again, it really just depends on what kind of queries you're expecting. If it's exact match, you want BM25, or if it's close to exact match. If you want something a little bit more vague, a little bit more conceptual, you can do vectors. And if it might be both, then hybrid is probably the way to go. I would say that in the majority of cases that I see, hybrid is probably, the way to go, but even then you still raise other questions about like how much do you want to go with hybrid, or how much do you want to go with vector versus how much do you want to go with BM25? So it's all just going to depend. Yes.
You also recommend that for like documentations, like search for docs?
Yeah, I would say that if you want somebody to get like the documentation is very specific, it's very, it's very precise. In that case, I would probably say that you want to lean more towards like BM25 instead of vectors, for example. Yeah. Yes.
What's the tax for hybrid?
I'm sorry, I couldn't
What's
get
the tax for hybrid?
the tax for hybrid. It takes longer. You are running two parallel searches essentially, so it's going to take that much longer. And on top of that, you also need to run the RRF algorithm to merge them together. So there is, then you start getting into questions about latency, is this worth it? Things like that. So yeah, nothing comes free, unfortunately.
So it's like 2x, 3x.
I don't want to lie to you. Honestly, I'm not exactly sure about like the exact number. It would depend on how you're weighting the two different ones. So if it's like a 50-50 split versus like 60-40, that's going to meaningfully affect things. Also depends on how many dimensions that your vectors are being embedded in. Is it 100, dimensions? Is it 700? Is it 2000? That's also going to, meaningfully affect things. There's just way too many variables for me to be able to give you like a clean answer on that.
Is there a way to cut off one if it looks like the other one is coming with better results?
Yeah, so you can implement systems where you are determining at like runtime if a user searches for something, you can have ways of determining, oh, this looks like it would be better for vector search, this would be better for BM25, or this would be better for hybrid, essentially. So you can make, semi-intelligent guesses about which of those methods might work the best under different conditions. Okay, cool. Any other questions? All right, awesome.